Hi and good day to Encik Kamal and Dr. Hazli. My name is Weng, and today I would like to present my final year project which titles Simulations of Melt Flow Properties of ABS-hBN Composite in Fused Deposition Modeling's Nozzles. 3D printing is an additive manufacturing process of building a two-dimensional model by using digital model data. There are several examples of additive manufacturing including FDM, LOM, and SLS. The material usually used in additive manufacturing are the ABS and PLA. So I would like to explain the material deposition systems of FDM because in this project the simulations approach is conducted in the FDM nozzles which consists of liquefier and the outlet of the nozzles. So firstly the solid filament is wounded at the material's poles. The filament is then being pushed mechanically into the liquefier. Then the heat generated by the heater's elements melts the filaments. Then the melt is being extruded through the nozzles with pressure applied by the incoming material. The melt flow is presented in parabolic forms due to the actions of the material onto the walls. In this project, the first problem statement is the melt flow's behavior of the material affects the extrusion process stability and contributed in quality of the final product. The second problem statement is the additions of filler into polymer for the purpose of FDM filament changes the melt flow properties of the polymer filament. So the first objective in this project is to simulate ABS flow in FDM nozzles using ANSYS simulations, and the second objective in this project is to analyze the effect of HBN failure on the velocity and temperature of ABS-hBN composite melt flow in the FDM nozzles. The tools that used in this project is through the simulations approach. ANSYS Fluence. Fluence is used for the simulations in liquefier, and ANSYS Polyflow is used for the simulations in outlet of the nozzles. Both of these simulations are studied separately in the considerations of the correlations, successive correlations. This is because the feed material that undergoes through the phase transitions is subjected to complex thermal and fluid flows in FDM. So normally in ANSYS fluence is used to predict the fluid flows, mass transfer, and heat and chemical reactions. And in ANSYS polyflow is normally used for the extrusion process, thermoforming process, and glass forming process. So this is the process flowchart of the entire project. So the first stage of the material depositions process is the melt flow in the liquefier. The geometry and meshing generations of liquefier are shown as in the figure below. The liquefier is constructed in design modeler based with the dimensions which based on the real life product, and the liquefier model consists of hundreds of 50 millimeters long tube with an internal bore diameter of 1.83 millimeter. The second stage of the material deposition process is the extrusion through the nozzles. The geometry and meshing generations of a nozzle model is constructed as in the figure below, and the nozzle's outlet model is constructed in two-dimensional axis-symmetric model. The mesh is refined in the conical sections in order to capture the changes of flow in the specific region. Next is about the material property setups in the simulations model. ABS is chosen as the testing material, and the HBN is selected as the filler material. The table below tabulated the material properties of ABS which apply in the simulations model. The flow characteristics of the ABS and ABS-hBN are identified through the Rheology data based on the finding of Devaki. The viscosity of ABS and ABS-hBN in a simulations model is depending on the shear rate. The shear rate dependence of viscosity approach follows the power law viscosity model as shown in the equations below. The N symbol is represented as the viscosity, the symbol Y is shear rate, and K and N are the power law fit parameters. And the rheology data of the shear rates at hundreds is used as the input data for simulate and compare the melt flow behavior of ABS and ABS-hBN. The following shear rates rheology data of ABS are used for the volumetric flow rate measurements and velocity measurement. So the thermal boundary conditions and flow boundary conditions are applied at three phases of the simulation model, which the entry phases, the wall phases, and the axis phases. The FEA simulations started from the entry of liquefier applied with velocity inlets and the axis of the liquefier applied with pressure outlets. The temperature is set in kelvins at the entry and at the walls of the liquefiers. No slip conditions is selected at the wall because the melt of material is considered adhere to the wall and the expressions of temperature expressed in every single flow sections in the liquefier. So for the outlet of a nozzle model, since the entrance of the nozzles is equivalent to the exits of the liquefier, the volumetric flow rate which obtained from the liquefier model is applied as the inflow at the entrance of a nozzle, and outflow conditions is selected at the end of the outlet of nozzles model. The temperature is applied in the entry of the models and same as the liquefier model. No slip condition is selected at the wall and heat flux is applied as the thermal boundary conditions at the wall. Temperature control and pressure controls are the simulation results in liquefier. The red regions shows the maximum value of temperature and pressure value, and while the blue regions shows the minimum value of temperature and pressure. Based on the temperature control result, the temperature at the end of the liquefier is approximately 508.4 Kelvin, and since the melting temperatures of ABS is 230 degrees Celsius, which in 503.15 Kelvin, the desired melting temperature of ABS material is achieved before the melt flow reach the axis of the liquefier. So based on the simulations, there is a sufficient space for the material to melt evenly and completely in the nozzles at the optimum extrusion temperature. For the pressure difference in the pressure control results, will be taken to find out the volumetric flow rates by using the Poiseuille's law. The temperature control and pressure control and velocity controls are the simulation result in outlet of the nozzles. As mentioned before, since the entrance of the outlet of nozzles is linked to the exits of the liquefier, the entrance of the nozzle recorded the highest temperature and dropped slightly throughout the nozzles in the temperature control results. This is due to there is no heating elements to supply and maintain heat during the melt flow. So for the pressure control result and velocity control result, the melt flow moved from the lower velocity to higher velocity and produced pressure drop in the model. Based on the theory of continuity equations, the fluid speeds up when it enters the constricted regions. So within the nozzles that tanges diameters, the regions where the fluid moving slow will be under high pressure. And based on the Bernoulli principles, the points of the slowest speeds produce the higher pressure than the points of the faster speeds. So therefore, the pressure in the entrance regions have the larger pressure produced than the exit region. Next is about the volumetric flow rate measurement. Due to the ABS is incompressible in the liquefier and the outlet of the nozzles, the fluids flowing through the models could change shape, but the amount of volume is still maintained. So the pressure difference from the pressure control results of the liquefier is used to obtain the volumetric flow rates of the melt flow in the entire systems. The volumetric flow rates is measured by the using Poiseuille's law as shown below, and based on the graph, the volumetric flow rate is inversely proportional to the viscosity. Viscosity is known as the resistance of the fluid flows, and as the viscosity increases, the thicker the fluids, and causing the volumetric flow rates of the fluids decreases. Next is about the velocity measurements. The velocity result is recorded from the simulation control result of outlet of nozzle models. As the volumetric flow rates of ABS in the outlet of nozzle increases, the average velocity of the fluid increases. The relationship between the volumetric flow rates and average velocity can be explained in the equations below, which Q equals to volumetric flow rate, A is the cross-sectional area of flow, and V is the average velocity. As mentioned before, due to the melted ABS is incompressible, the flow rates does not affected by the cross-sectional area of the regions, but has the effect on the overall average speed. Next is about the additions of HBN in ABS. Based on the research finding, additions of HBN in ABS increase the thermal conductivity of the composite material. The graph below plotted the thermal conductivity of ABS-hBN increases with the increasing of weight percentage of additions of boron nitrides. So for the simulations in this model, the thermal conductivity of ABS-hBN obtained from the 5% of weight percentage of HBN is used as the input data value for the simulations. So as the thermal conductivity increases, the rate of heat will increases and improve the heat conductivity of the material. So as you can see in the temperature control results, the ABS-hBN required lower melting temperature than the pure ABS. The melting temperature of ABS-hBN is around 218.0.808 degrees Celsius and in 491.223 Kelvin. The desired melting temperature of ABS-hBN is achieved before the melt flow reach the axis liquefier. Based on the velocity control results, the maximum velocity obtained in ABS-hBN is larger than the in ABS. This is because under the shear rates of hundreds, the viscosity of ABS is higher than the ABS-hBN. Therefore, the ABS-hBN has the higher velocity flow obtained as compared to the ABS. In conclusions, as opposed to the objective, the melt flow behavior along the liquefier and outlet of nozzle has been successfully simulated by ANSYS simulations. The results are presented in temperature, pressure, and velocity control. And as the viscosity of fluid flow increases, the volumetric flow in liquefier decreases. So the higher the volumetric flow rate, the higher the average velocity of the melt flow. Second, the additions of HBN in ABS improve the properties of composite material, which thermal conductivity of ABS-hBN increases, and it requires lower melting temperature to melt and lower velocities of melt flow as compared to ABS. Throughout this project, the project potential is it can predict the melt flow behavior of pure ABS and how HBN additions changes the properties. And it helps to reduce the numbers of experiment trial and optimize the varieties of composite material during the fabrications of filaments. It helps to reduce the wastage of experiments and save time for the researchers. And that's all from me. Thank you.